Alright, so today's topic is section 3.2, Dyck path and Motzkin path. So these are two well-studied lattice paths, and these will be very important tools when we study orthogonal polynomials later. So we will first look at their definitions and some of their properties. So first, there are examples of lattice path. So we will define a lattice path first. A lattice path from, say, U to V is a sequence of points. Sequence, say, V0, V1, dot, 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 Vn, sequence of, say, points in Z times Z. So we will consider X, the points in R2 whose coordinates are all integers. With, of course, it starts from U, so V0 is U and Vn equals V. Okay, so we want something like that. So lattice path is nothing but a sequence of integer points. That's all. Simple, right? And each pair, in this case, each pair, Vi plus 1 is called a step. Okay, so we have a, the initial point is this, and this is one step, and this is another step, etc. And we will also sometimes it's quite common that this step is identified with identify. We will treat this the same thing as just this. So this is a component-wise difference. It's like a vector subtraction. Okay. So element as Z and Z. Okay, I'm going to give you some examples, but let me define Dyck path. So a Dyck path is a lattice path with some properties, of course, consisting of two types of steps. There are two types of steps, which I call up steps. Up steps are going to be steps of this form, 1, 1, and down steps, steps of the form 1, minus 1, staying weakly above the x-axis. Weakly means it may touch the x-axis, but it will never go below x-axis, okay? And example. Yeah, maybe a grid would be nicer. Okay, so let's say we start from the origin, and this step, this is 1, 1, so this is 1, 1, 2, 3, 4, like that. So this is an up step, 1, 1, and 1, 1, up step, down step, but you cannot go below like that. Okay, so up step, something like that. So this, the ending point here is now 7.3. So this is a Dyck path from 0, 0 to 7, 3. The Dyck path is something like that. So it may also start somewhere above or somewhere anywhere. So this is a kind of a general definition. And we're gonna write this notation. Dyck of U to V is a set of all Dyck path from U to V, okay? And also, because most of the time we will be interested in Dyck path from 0, 0 to 2n, 0. So I'm gonna use this notation for that. So this is Dyck path from 0, 0 to 2n, 0. You know, it must be an even integer because otherwise you cannot really reach the x-axis again. So if you go back to the x-axis, this must be even, right? That's why we only consider even number here. All right, so these are Dyck path. So the question is, can we enumerate this? So question, what is the cardinality of this? Yeah, this is a very well-known number, and also there are many ways to compute this, but we will find a formula for this using generating functions because it's a good exercise to use generating functions that we learned recently. So let's try to do that. So let C of x to be the generating function for the Dyck path of size 2n, n greater than or equal to 0, x to the n, like that. Okay, so let's find a formula for this generating function. But what is the generating function? Generating function for sequence, like an, then generating function will be an, things like that. But for us, it's more useful if you think of a generating function as a way of listing all combinatorial objects. So, in other words, this is the same thing as generating function for all Dyck path. Let me write this as a set of all Dyck path from 0, 0 to 2n, n for some non-negative integers, okay? So just consider all of them and add them together with a weight of pi. But what is the weight? Weight of pi is, I'm going to define x to the number of down steps or up steps, the same. Okay, let me define it this way. Then this is equal to this, because if you collect all those weights with x to the n, that's going to be exactly, there are exactly these many terms, so this is equal to this. Do you see they are equal? So yeah, so I think it's more useful if you consider generating functions in this way instead of just this. This is just a formal definition of the generating function, but this, and even furthermore, you should really think of this as the image of picture that all the Dyck paths are drawn. So, for example, there's a Dyck path of length 0, which is just the single point, and Dyck path of length 2n, you can only go like that, right? Because you cannot go below. And Dyck path of length 2, you can go either this way or this way, all right? And Dyck path of length 6, maybe I should start like this. The order is not important. You can generate them all yourself, right? And etc. Okay. And what I want you to think about this is that imagine all of this in your head, and this, what is the weight of this? The weight is the length or half length or the number of down steps or up steps. So it's going to be 1. And this, the weight is x. The weight of this is x squared, x cubed, x cubed, x cubed, like that. Okay? So if you collect them all, then that means C of x is 1 plus x squared, and etc. But that's if you collect them all with the same weight, then you get formulas like this. Or just first few terms look like this. Okay? So this is our generating function. And so how can we find the formula for this instead of just listing just a few terms? So now we can investigate what these look like. So C of x in this picture, you see we have one Dyck path of length 0, which will give you 1, right? But otherwise, it will always start with an up step, right? So either it is 1 or it must start from an up step. And because everything must be something from origin and to end, it must return to the x-axis, right? So look at the first time it reaches the x-axis. We don't know when, but it will eventually reach. But this is not the end, right? This is the x-axis. It may continue, right? So it may go something like that. So every Dyck path looks like this. Either it's an empty Dyck path, or it goes up and then it stays somewhere above and then it goes down, and then you do the same thing over here. That means here, everything in between, it can be any, say, sigma in the Dyck path. And here, any tau can appear here. It could be empty. Empty means it ends here. That means, imagine your picture. You have 1 plus and everything here that can be collected in this way. So whenever you give one Dyck path and then put it here, and then another Dyck path and put it here, you get a Dyck path. That means if you collect them all nicely, then this is going to be 1 plus. This will give you a generating function for Dyck path, which is C of x. And this will give you a weight x, because the weight of a Dyck path is the number of down steps, x to the number of down steps. So this will give you x, and this will give you another Dyck path like that. So this is how you get a formula, functional equation for a generating function that you are considering. So if you are not convinced, just imagine the picture here. This picture is inside, this picture is inside. So the way we multiply formal power series is that for each factor we select one term. Here we select x, here we select something like that. And they will give you a way to make one Dyck path here. So that's why it is equal to this. Is this okay? So now we have an equation that, let's write c. We can rewrite this like c, x times c squared minus c equals 1. I rewrote this using like this. Oh, sorry. Yes, I want this to be plus 1 equals 0. Okay? Now we can solve this equation for c, just because it's just a quadratic equation. So c is 2x over 1 plus or minus square root 1 minus 4x, right? So the generating function must be this. But we have to select the correct sign. Is this plus or minus? But that can be this sign can be obtained if you compare the constant term both sides. So the constant term is c of 0, which is just imagine that you plug in x equals 0. Then it's going to be 1 plus or minus 1 over 2x, right? So, but this is what? the constant term is this. This is 1. So this must be, oh, sorry. No. Yeah. Okay, let me write, this is not very accurate, but let me write this way. If this is plus, this doesn't make sense because you cannot really divide this by 0. But if this is minus, then maybe we can make this make sense of this. So in fact, that's the case that because in fact, this starts with 1 plus something x like that. So if this is minus, we can cancel this, and then we can also cancel x as well. So that means we have to select plus is a minus here. So minus is the correct sign. So minus is the correct. Okay. In other words, our conclusion is not yet, but we reached one milestone. It must be minus. All right, now what? Now we can use the many properties of generating functions or formal power series. Those power series can borrow things from there. So what is this? 1 minus 4x and square root. And this is 1 minus 4x 1 over 2. But we can use the binomial theorem. So it's a binomial theorem. Says that sum 1 plus x to the alpha equals sum over n greater than 0, alpha choose n, x to the n. Where alpha choose n is, alpha can be anything, not necessarily an integer. Alpha minus 1, alpha minus n plus 1 divided by n factorial. This is the binomial theorem that you learn from calculus, and you can actually use it. In fact, we can make everything completely formal, and then we can prove this just formally, but I'm not gonna go into that details, but we can just borrow this theorem from calculus. So we can just be happy about that for the moment. So then we can compute this, right? This is summation n 1 over 2 choose n minus 4x to the n. All right? Now what? We do just a computation. Now it's all about just computing things. Like 1 over 2. Now this minus 1, so it's minus 1 over 2, and minus 3 over 2, and the last one is minus 2n minus 1 over 2 over n factorial. And let me separate these things like minus 1 to the n, 4 to the n, x to the n. Okay? Then how many minuses do we have here? N minus 1, minus signs. So this will be minus. We can cancel all the minuses here and then with this and leaving only one minus. And also, if you multiply 2 to the n here, in each factor, you can forget about the denominator. That means we have 1 times 3 times 2n minus 1 over n factorial and 2 to the n, x to the n. Okay? Now what? If we multiply like 2, 4, 2n, or 2n minus 2, then we can make this like just a factorial, right? So I'm gonna make this as, okay. But, okay. Let me do this in 2 steps. One, I'm gonna separate 1 because it's a little strange if you have 0 here, okay? So if n equals 0, this is 1, right? So I separate this here, and now n is greater than or equal to 1 because, you know, it's somewhat strange to consider this when n equals 0. So now I'm gonna replace, multiply, imagine like n minus 1 factorial imagine that we multiply here and there n minus 1 factorial. We can do that because we multiply the same thing. And then if you multiply this and this, that's exactly what we want. 2, 4, 2n minus 2, right? So then we will get something like n factorial, n minus 1 factorial, and 2n minus 2 factorial, and then 2 times x to the n. Is that right? And this is really a binomial coefficient, so eventually this is 1 minus, I don't know, 2 times n greater than or equal to 1. This is 2n minus 2 choose n minus 1. Let me write it this way, x to the n. But if you rewrite this, you get, this is, now I'm going to plug this into over here. So 1 cancels, and then minus, minus, plus, and then these 2 cancels. So everything becomes nice. So C of x is going to be n greater than or equal to 1, 1 over n, 2n minus 2, n minus 1, x to the n minus 1. But we can shift this n, then we get 2n n x to the n. But what does that mean? This was the generating function for the Dyck path, 2n x to the n, right? That means two generating functions, two formal power series are equal. That means all the coefficients are equal. So we get this result. So if this is your first time to see computation like this, you may think this is complicated, but this is a very routine procedure. So once you get used to it, it's just almost automatic. You can even do this with computer. So we can do this. We can get this formula just for free, almost for free, once you know all the techniques. And this number here is called Catalan number. So Catalan number the Catalan number is Cn, and it is just the number that we saw. The first few numbers, C0, C1, if you compute this, then it's like, it goes like 1, 1, 2, 5, 14, 42, 132, 429, So Catalan numbers are one of the most well-known numbers in combinatorics. It appears like everywhere. So there's a famous mathematician, in combinatorics, Richard Stanley, and he collected more than 200 combinatorial objects counted by Catalan numbers. So Catalan object. So Dyck path are one of the Catalan objects, right? And there are many more. And some well-known Catalan numbers, Catalan objects, like a Dyck path, of course. And what did I? Yeah, some of them are almost the same. Ballas sequence and diagonalization, triangulation of n plus 2 gon. Maybe I should write of length 2n. ballot sequence of length 2n, triangulation of 2n plus n gone, n plus 2 gone, and a binary plane, binary trees with n vertices. So maybe I should, for example, ballot sequence, let me write, this is 1, 2, 3, 4. So we already saw 1, so 2. Ballot sequence is like sequence of A's and B's with 2n. So there's a vote with 2n from 2n people. So you got this vote, and we have 2 candidates, A and B, and so we have collected the 2n votes from the 2n people. So each time you look at the vote, and it's going to be A or B. And the thing is, they have the tie at the end, but A is always at least the same or ahead of B. So that means as a n equals 2 example, maybe n equals maybe 3 is like A, B, B, B. So they are tie at the end, but A is always at least as many votes as B. So also like A, B, B, etc. like that. And third triangulation. This is a nice diagram. So n equals 3 is going to be a pentagon. So there are 5 ways to triangulate pentagon. Like this. And plain binary tree means we also have to look at the left. So it starts from the root, and it may have a left child or a right child or both. So it has 3 vertices, so it may have this or this, or this. There are 5 objects like this. So there are many Catalan objects like this. So there's a book written by Stanley, so you can, if you're interested, you can check that out. And in fact, nice result of the Catalan numbers is that they satisfy a nice recurrence. If n is greater than or equal to 1, Cn equals sum over k from 0 to n minus 1, Ck, Cn minus 1 minus k. And this can actually be proved using the decomposition that we have over here. Everything, if this is length n, and then you can decompose into 2 parts like this. And if this has length k or length 2k, then this will have length n minus 1 minus k. That's why we have that Catalan recurrence. So if you using only this recurrence and the initial condition, C0 equals 1, you can compute all the Catalan numbers, right? Because C1 is C0, the C0, so it's 1. C2 is C1, I think that's right, yeah. This is C1's, their sum must be n minus 1, so this is 2, and C3, C2, C0, C1, C0, C2, so it's 2 plus 1 plus 2, which is 5, that is as we saw. In this way, you can compute all the Catalan numbers. Okay, so these are Dyck path. Now, let's look at Motzkin path. So Motzkin path is quite similar to Dyck path. The only difference is we have another type of steps allowed. So a Motzkin path is a lattice path consisting of, so up steps as before, 1, 0, down step 1, -1, and horizontal step 1, oh wait, this is 1, 0. No. So it may go up like this, like the Dyck path, and also go down like that, and it may also stay in the same level like that. So example, oh, of course, with staying above weakly above the x-axis. So for example, yeah, it may start everywhere. So let me say this. It may stay in the x-axis. This is an example. And as usual, mod u to v is going to be the set of all Motzkin path from u to v, and mod sub n is going to be the Motzkin path from 0, 0 to n, 0. Now n does not have to be even. It can be, because you can go just horizontal. You can use horizontal steps. Okay. Can we enumerate Motzkin path? What is the cardinality of the Motzkin path? But if you think about it, you can use Dyck path. So how can you get a Motzkin path from a Dyck path? Just start with a Dyck path and then just insert some horizontal steps there. Then you will get a Motzkin path, right? So for example, start with some Dyck path, insert some maybe 2 here, 2 horizontal, maybe here just 1, here 3, then what do we get? Up, I inserted 2 horizontal like that. Here and horizontal, I think I inserted too much, so let's not insert this. So here we have a Dyck path, here we have a Motzkin path, right? That means you can select K and then Dyck path with 2K, because the length must be 2K. So 2K must be less than or equal to N. So 2K K is from 0 to floor of N over 2. But once you have this, there are in fact 2N positions. Then you have to select the positions for the horizontal steps. So it's going to be 2N choose K. So in this way, you can construct the Motzkin path uniquely. So first, consider a K such that it's less than or equal to this, and then choose the positions for the horizontal steps, and then the remaining steps you just make a Dyck path. But this is Catalan number, so you can replace this by the CK, like that. So this is a formula for the number of Motzkin path. It doesn't have the single term formula, so it's a summation. And we can find a generating function for this. Sum over n greater than or equal to 0, Motzkin path x to the n is equal to 1 minus x minus square root 1 minus 2x minus 3x squared over 2x squared. Proof is quite similar to the proof that we saw for the Dyck path. Or you just need to find a functional equation. So proof. Let me just sketch the proof. Let left-hand side be m of x. So this is m of x. Then imagine that this is a generating function for all Motzkin paths. So you list all the Motzkin paths. And what is the weight? The weight must be the length, the exact length. So in other words, number of steps. And can you find a functional equation? Let me just write m, just for short. Either you have an empty Dyck path, Motzkin path, or if it's not an empty Motzkin path, there are two choices now. First step is up step, or first step is a horizontal step. Let's consider the horizontal step. If it starts with a horizontal step, there will be another Motzkin path over here. Or if it's an up step, if the first step is an up step, it will stay somewhere above, and then eventually it will return to the x-axis, and after that it can go something as much as it wants. So, but this part, this is 1, this is x, this is m, this is x, this is m, this is x, this is m. So m equals 1 plus xm plus x squared m squared. So if you solve this equation for m, then you will get this. Of course, it's a plus or minus, so you have to choose the sign carefully, then you will get this minus sign there. So that's the generating function for the Motzkin path. Okay. So Motzkin path, this will be a very, very important object in our study of combinatorics of orthogonal polynomials. So because we will see later that the moment of an orthogonal polynomial is going to be a generating function for Motzkin path with some weight. We will see that later. So this will be a useful tool. Question?
I think we should have n choose 2k and 2n choose k.
Oh, yeah, that's right. Yeah, thank you. And choose. Yeah, there are n. We have to select 2k. Yeah, thank you. Any other questions? All right. Then let's move on to the next section. Set partitions and matchings. So these are actually fundamental objects in combinatorics. So it's possible that you have seen this somewhere else. Especially set partition it's not only it's important not only in combinatorics, but you basically see this everywhere in mathematics. So, or even in real life, partition. The definition: a set partition, or sometimes just we say partition. So a set partition of a set X is a collection pi, which I write like b1 dot 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 bn, collection of let me use k. It's not important, but that's collection of subsets of X. So each bi is a subset of X, such that satisfying the following conditions. So first, they must be non-zero, non-empty for all I. And they must be non-intersecting. Intersection must be empty for all I different j. And finally, their union is the whole set X. Partition is like that. So it's really, you can imagine if X is like that, then partition means, you really partition things like that. Set partition is like that. And each BI is called a block. Okay. And we will be interested in set partitions of n, right? Set partition of n. This is the set of all integers, 1 up to n. We can visualize this using a diagram. It can be visualized like this. So for example, let's say set partition example. Maybe just an example. Pi is like 1, 3, 5, 6. Say 2, 7, and 4. Okay. So it's really simple. We put dots like 1, 2, 3, 4, 5, 6, 7. You put the dots like this, labeled 1 up to n. And then if you see a block like this, you just connect the dots like 1, 3, 5, and 6. This is one block, and 2 is connected to 7, and 4 just stays there. So this is a set partition. This is a visualization of this. So we can easily identify these two. And I'm gonna write pi definition. Let me write pi n. In capital pi n is a set of all set partitions of n. Okay. And by the way, pi 0 is going to be this. Does this make sense? So basically, yeah, we can just say that we define this, but empty set also satisfies, it's a collection of nothing. So it satisfies all of this. So it's like set partition of empty set. So the set partition of empty set, there's only one set partition of the empty set, which is this. Which is this. So it's the set of this, so it's like this. So I feel like I'm teaching set theory. Anyway, so pi 1, it's kind of confusing, you know what I mean. I think this is the right way. But we are not doing set theory here, so just imagine that we have this. Yeah, let's not write this. I think that's correct, but the point is we just consider all collection of all set partitions of n. Okay. Oh, and let me define one more thing. Pi sub n comma k is a set of all set partitions of n with k blocks. Okay, that's the. And finally, we define this. The Stirling number of the second kind, Stirling number of the second kind. The Stirling number of the second kind is denoted by capital S of n comma k, which is the cardinality of this. So in other words, it's the number of set partitions of n with k blocks. So let's compute some of these. First example, as n equals 0, this is 1. But otherwise, it'll be 0. So maybe I can write k delta k 0. So this is 1 if k is 0, but otherwise it's going to be 0. Because there's only one set partition of the empty set, which is the empty set. So it's, and also, what is S of n comma 0? This must be also n0. If n is non-zero, there is no set partition with no blocks, right? So it's also true. And what is S of n comma n? Set partition of n with n blocks. Each block must have only one element. That's the only possibility, so it's always 1. And what about S of n comma k with if k is bigger than n? You cannot make a set partition with more blocks than the cardinality of the set, so it's 0. So, in other words, this is non-zero only when k is between 0 and n, right? Otherwise, if k is outside the range of from 0 to n, it will be 0. And there is a nice relation, a recurrence relation for the set partitions for nk greater than or equal to 1, Sn k equals Sn minus 1 k plus k Sn minus 1 k minus 1. Proof is really simple. If you understand the definition, it's almost immediate. What is this? So, okay, let's say this. This is the cardinality of this set, right? Set partition of n with k blocks, right? So, just consider one set partition there. And consider two cases. Case 1. Just look at n, the largest integer n, and see what the role it plays. So n is a singleton. If n is a singleton, then just ignore n. Then you have n minus 1 integers with k minus 1 blocks. So that means if you delete, if you let me write this way, removed will be element in n minus 1, k minus 1, right? But otherwise, case 2, otherwise. So this is not a, this itself is not a set block. That means it is in a block with something else. So then pi with n deleted, this will be a set partition of n minus 1, but you removed n, but there are still elements in the block, so the block still stays. So we have still k blocks. So if you just add this integer n into one of these blocks, then you will get this back. So that means there are k times Sn minus 1 k possible such set partitions. Because this set partition is always obtained from this by adding n into one of the k blocks. So that's the proof basically. So this is Sn minus 1 k minus 1, and this is this. So we just add them together. Oh, sorry, this is just n. So that's going to be this. Okay, so it just follows from the definition. Yeah, there are many properties of the set partition, so I'm not gonna list them all, but I think this is it's useful to know this. S and K has a formula like this: 1 over k factorial, I from 0 to k, minus 1 to k minus I, k choose I to the n. Looks a bit complicated, but once you know the idea, this is quite simple. There is a nice connection between set partition, these Stirling numbers and number of functions. What is the number of all functions? F from n to k. Sorry, onto functions. What is the number of onto functions? How can you compute the number of onto functions? That means you have n elements here. You have k elements here. Onto means it must hit 1. Also, it must hit 2, etc. So everything has its image, right? And the image must be a set partition of n. So this is S. So you basically partition the whole set into k parts, k blocks. But we have to assign which one goes to 1 and which one goes to 2. So we have to multiply k factorial. So this is the number of onto functions, right? But you can compute the number of onto functions using the principle of inclusion and exclusion. Onto functions, on the other hand, is also equal to by principle of inclusion exclusion. This is also equal to sum over all I from 0 to k. Okay, so instead of computing all onto functions, you first compute things that goes from here to everywhere. I mean, just compute all the functions. That will be, we have k elements. So each element here, we have k choices. So it's going to be k to the n. But that's not going to be the right answer because some of these will be missing. So so now we subtract things that doesn't have 1 in the image. But that's going to be k minus 1 to the n, etc. So that in generally, the principle of inclusion exclusion says that you consider all functions from this to I elements here. That is I to the n. And the number of ways to select the range is n choose k. K choose I. So this is the inclusion exclusion thing. So you add and subtract and then do this over and over, then you get the right answer. And because this is equal to this, because they counted the same thing, so we get the formula that we want. So that's the proof. Okay. And now let me.
이그레이션 봐봐. 그냥 프로퍼티에 Sn 마이너스 1, K 앞에 K가 가야 되지 않습니까?
Yes. Sorry about that. This -1. Is that right?
그러면 프로프도 이제
-1. And also here, this is okay, right? This is okay. Yeah. This is okay. Yeah. Thank you. Yeah, you should be able to correct all the typos here. That's your exercise. Okay, so you remember this. This is a useful thing to remember. Number of onto functions is k factorial times s of n comma k. Now, let me define another definition. A following factorial is something like this. The notation is x sub n. This is defined to be a product of x, and you decrease x by one at a time, and then you multiply them all. So we have n factors like this: x minus 1, dot, dot, dot. It's following factorial because it's decreasing. There's also a rising factorial, but we don't need them, so we only use the following factorial. And there's nice formula like this: k from 0 to n, s of n comma k. If you multiply following factorial here, then you get x to the n. So as a identity as a polynomial in x. Yeah, so let's prove this. But there is actually an interesting thing going on here. We have to prove this as polynomials in x. So x is not an integer, x is just a variable, right? But we may assume that x is a positive integer. I'm going to prove this assuming that x is a positive integer. And then I just say that's enough. Is that enough, do you think? If it's true, but if I prove this, it's an integer, so arbitrarily positive integer. So we will, if you prove this for a positive integer, we will see, we can check that. I mean, we will know that this is true for all positive integers x. That means this has infinitely many solutions. So just subtract this minus this has infinitely many solutions in x. It's only possible when the polynomial itself is 0. So that's why we may assume x is a positive integer. So we assume x is a positive integer, and then we prove this identity by counting things. Okay? So what is the left-hand side? So we know that this, okay. Let's consider right-hand side first because that's easier. This is the number of functions, all functions, f from n to x. X is an integer, so it makes sense to write things like that. This is the number of all functions. Okay. Now we will consider. We will separate this as a sum k from 0 to n. Number of all functions according to the size of the image with k elements in the image. Okay, so of course this is true because the image can have elements either from 0 to n. Okay. But can you compute this? So if you want exactly k elements in the image, then you can do this by selecting those k elements. How many ways? Let's do it this way. So just imagine the diagram again. 1, 2, dot, 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 n. 1, 2, dot, 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 x. So you want this to have image k elements in the image, right? That means if you collect the image, then they will form a partition of n with k parts, k blocks. So that's S of nk. This is for select partitioning this into like k parts. But once you did that, you have to map this into one of the elements there. So the first block can have like x choices because it can go anywhere. But once you decide the first block, the image of the first block, the second block has only x minus 1 choices because the first one this cannot go to the same element. So, and etc. So the last one will go into x minus n plus, k plus 1. So that's exactly x following factorial. But that's the proof. This is n factorial, x to the n. Maybe let's write this way, x to the n. So x to the n equals this, and this. That's this. Okay, so, right, maybe I can do this here. Now matching. Matching is really a simple thing. It's a special kind of set partition. A matching on a set X is just a set partition of X with blocks of size 1 and 2. 1 or 2, let's say. 1 or 2. So every block must be of size 1 or 2. If that's the case, then we say that that's a matching. And a block of size 1 is called a fixed point of the matching. A block of size 2 is called an edge or an arc, because we want to draw an edge or an arc above these two elements. And if there are only blocks of size 2, then it is called a perfect matching. Or complete matching. Perfect matching or complete matching. So for example, using the diagram, 1, 2, 3, 4, 5. So this is more complicated. This is an example of a matching, right? We have two edges and one fixed point. Okay. And what about 1, 2, 3, 4, 5, 6? So an example of a perfect matching is something like that. There's a perfect matching. So in order to have a perfect matching on a set X, the cardinality of X must be even, of course, right? Then what is the cardinality of the perfect matchings then? The number of complete matchings, perfect matchings, or on 2n is which we write 2n minus 1 double factorial, which by definition is 1 times, 3 times, 5 times 2n minus 1. So it's like it decreases, it starts from 2n minus 1 and decreases by 2 each time, all the way up to 1. And what about the number of matchings then? Not necessarily complete. Now you see, you find fixed points, and then the remaining things must be a perfect matching. So k from 0 to n over 2. Among n, you select 2k elements for fixed perfect matchings, and the remaining things will be fixed points. And you, among these 2k integers, you find a perfect matching, which is this. So it will be 2k minus 1 double factorial. So yeah, I just proved this using this, So let's prove the first one. That's going to be enough. But this can be done quite easily if you consider how a complete matching is constructed. So just imagine 1, 2, 3, 4, 5, 6, like 2n. How do you construct a perfect matching? You have to connect the last integer to some of the previous integers like that. How many ways to connect 2n? There are a number of ways to connect 2n with an integer. Is of course 2n minus 1, because it can be connected to any of these previous ones. But once we have done this, we are left with 2n minus 2 elements. And you do the same thing. Number of ways to connect the max remaining integer with another remaining integer is 2n minus 3. You go something like that, so the number is going to be like that, as we wish. Okay. Yeah. So in this section, we learned set partitions and matchings, and recall that we defined starting number of the second kind. So you will probably have wondered, what about the first kind? And we will learn the first kind, starting number of the first kind in the next lecture, and that will be related to permutation. Okay. All right, so then I will stop here.